Paolo, thank you, the organizers, first for the introduction, for the invitation. And yeah, my apologies that this talk is probably a bit different from the previous talks, or from most of the previous talks. There's rather probability and not so much genus or topological recursions that will not appear. There is just one word that probably is similar. That's the word hyperbolic, but other than that there is some graphs and tail bounds, and even the word hyperbolic appears in a different context, but I'll explain that. Okay, so first it's about hyperbolic random graphs, and it's a particular model of random graphs. Just one slide. What is the motivation? Well, the motivation of this model introduced by physics people is to model social networks, such as the internet, such as social networks, such as biological interaction networks, where there are many mathematical properties that appear in all these models, although these models actually come from very different contents. So these models are typically sparse, in the sense that if you're on Facebook or if you're on Twitter, then you have maybe 10 friends, or 0, or 5,000 at most. But it's for an asymptotic person, it's just a constant number. Then it's heterogeneous. That means it's not the case that everyone has the same number of friends, right? There is someone. It happens that most people have maybe 2 friends, or 0 friends, or 4 friends, but then there are some very important people that maybe have 5,000 friends, say. Then there is a phenomenon that these networks, what you observe in internet networks, in social networks, and in other networks, they're so-called locally dense, which means even though the graph in general is rather sparse, that you're not friends of most people in the world, you're just friends of a very few. It's locally dense in the sense that if I'm a friend of Elisabetta, and Elisabetta is a friend of Laurent, then maybe it's likely that Laurent and Elisabetta are friends themselves as well, right? So there is a kind of a clustering phenomenon that if A knows B and B knows C, then it's very likely that A knows C as well. And there is a small world phenomenon that was an experiment in the 60s by Watts and Strogatz, who showed that there is between any pair of people in the world, there is a connection of at most 6, right? So one was asked to send a letter to a person that maybe might know someone, that maybe might know someone, that maybe might know someone, that knows someone in the end somewhere in Africa, say. And the connection was 6, and this turns out to be the same in many social networks. So in Facebook, there were experiments that there is a giant component where most users belong to, that which is 4. Of course, there might be users, right, that are just on Facebook and they don't know anyone, or they're just 2 people that only connect between themselves and there is no connection with the outside world. But within the giant component, there is a small world phenomenon, which means that you can reach from any point quickly to any other point. It's navigable in the sense that when you want to send something to someone far away in Africa, then sometimes it's enough to know only the address of your neighbor, of your friend. So if I'm thinking, okay, I want to send it to someone in Africa, maybe I go to someone from here to Malta, say, and then the guy in Malta will send it then to someone in Libya, and then you go on and you reach South Africa, say, at some point. So only local information is already enough to tell you who to contact next. And finally, these networks, they're scale-free, so they have a power law exponent on the degrees, with an exponent between 2 and 3, meaning that there's a curve following a certain power law, meaning there's an exponent gamma, and the number of vertices that have k friends is like proportional to k to the minus this gamma. Okay? So these are models that we want to model. These are networks that we want to model with a model that is also susceptible to mathematical analysis. Okay, and people first started with random geometric graphs, in a sense where you just throw in your Poisson number of points in the unit square, and these points are vertices, and you add an edge between them if the Euclidean radius is at most some certain threshold. But this model is not so good, right? Because there is no parallel degree distribution. All degrees have all vertices have more or less the same degree. Here's an example of this with a certain radius. How this graph looks like. This is not really a social network because there's no big influencer on Facebook, no big influence on Twitter. This is relatively up to boundary effects, relatively homogeneous. So people said, okay, let's do the same thing, but instead of taking the Euclidean plane as a base, let's take the hyperbolic plane. There were physics people, Dima Kryukov and his group, that introduced this model around 12 years ago by now, well, in 2010. And the idea is just embed the points in the hyperbolic plane and take the hyperbolic distance between the 2 points as a measure of closeness of 2 points. Okay, so how could one represent the hyperbolic plane? Well, for example, there's different representations, but one model to represent the hyperbolic plane is the Poincaré unit disk. It's an open disk where these blue curves that you can see, these are geodesics. So for example, this line here, this is a geodesic in this model. This means that between this point and this point, the shortest line follows this line here, this curve here, and this is 90 degree. So this every one of these curves intersects the boundary at a 90 degree. Each of these heptagons here has the same area, so you can see that this heptagon has the same area as here, but because you see that there's many points close to the boundary and much less close to the center. So it's like a tree. One can think about it as a tree, but as a continuous analog. The points right at the boundary are at infinite distance from the center x, and if you want to convert the Euclidean distance to the hyperbolic distance from the boundary, then you can do that using this formula. So this is maybe one of the famous, don't want to say the most famous model of representing the hyperbolic plane, but maybe the most famous one. We do not exactly use this one here, or Kryukov didn't use exactly this model, but a similar model, which is the so-called naive representation, where instead of picking the unit disk, you take a much larger disk. The hyperbolic disk is represented by a ball of radius large, which will tend to infinity. So here we say it's represented as r squared. We represent it as a ball around the origin of radius capital R, where R will be large, will be tending to infinity. And a point P, so this point here, is represented in polar coordinates with a radius Rp and an angle phi p. And well, this model is such that if you want to compute the hyperbolic distance between this origin and the point, it's just this radius. For other 2 points, it's a bit more complicated, but I'll come to that. And just one thing of notation, so I'll denote by B0 of R the ball of radius R, the whole ball, centered at the origin O. Okay. So this is a ball of radius r, which has this perimeter, the hyperbolic sign. So the important thing is it's exponential in r. That's different from the Euclidean case. So you have here lots of space. You have a relatively small radius, but you can embed many points there because the space expands exponentially. Here is a connection between these two models. So it's kind of the Poincaré model is the small ball, and then you blow it up, and the distance y on the left side is a bit different, so you can convert it to the other model. So it's not true anymore that these lines are touching it right at 90 degrees anymore in the native representation, but other than that, it's a very similar model. It's just for calculation purposes a bit easier for us. Okay, so the formal definition that was introduced was not with the Poisson model, but it was really a uniform model, is the following. So we'll have exactly n points, n will be large. So it's always asymptotic results that we're looking at here. And then forget maybe about this nu for a second. Think about this as 1, but there's one parameter alpha, which is basically the curvature of the hyperbolic sphere. So if the hyperbolic plane, and then there is a ball, which if you think that you want to have n points and the space grows exponentially, well then you rather want to have a radius of the ball which is logarithmic in n, right? So that's what this capital R is happening here. So we forget about this mu for a second. So we have 2 log n here, and we look at the ball of radius basically log n around the origin, and then what do we do? How do we construct the graph? Well, we throw in vertices uniformly at random, independently in this ball. Of course, according to the uniformly at random, I mean in that sphere. So in that hyperbolic plane, so it will be much more likely to have points close to the boundary, and then we say two points are connected by each other. U and V form an edge E. If and only if U is in the ball of the same radius R, that's a peculiarity of this model, centered at the other vertex. Okay, so I'll explain that a bit more. So how do we throw in the points? Okay, so the angle is chosen, it's angularly symmetric, so the angle is chosen uniformly at random in the 0 to pi interval, and the radius independently of the angle is chosen according to this density given here. But the important thing is that this alpha appears here, this curvature, right? So if alpha is getting larger, then you have even more drift towards the boundary. So alpha, you could think about the number between 1/2 and 1, say. And if this R is getting larger, well then you have, or this capital R, then you see that you have something like e to the alpha R. So the larger alpha, the more you have drift to the boundary, right? Okay, so and then you kind of normalize so that this becomes a density. Okay, and then there's a soft version which says that you don't have to add the edge if and only if this one is in the ball of the other, but you could also say, okay, if they are close to each other, then the probability is higher. But I'm not gonna explain more about this model. This is just a generalization where you can incorporate temperature. Okay, so here's a kind of a color plot how the densities look like. So if alpha is closer to 1/2, okay, you see that there is a drift towards the boundary, but not so strong. But if alpha is getting larger, and if alpha is, for example, in the right picture, if alpha is 1 here, then you can see that there is a much higher density towards the boundary of the points. Okay. Okay, so how do we check whether there's an edge. Okay, if there is a point like and if you want to compute the distance from a vertex to the origin, then it's just the radius. The hyperbolic distance is just the radius by construction of this model. But if you have two different points, u and v, well, then you have to solve this hyperbolic law of cosine to get this difference between u and v. So in order to get this difference between u and v, which we call d, you just have to solve this. And if this distance is less or equal than r, the same capital R as the model, well, then the edge is there and otherwise not. Okay, so that's the model. And how did this graph look like? Well, like these. Okay, so these are simulations with 500 vertices and this intensity parameter 1 fixed. So you can see that if alpha is not so large, still there is a drift towards the boundary. There's more points around the boundary, but not so extremely as in this picture, right? And then if you draw the edges, you see, okay, these vertices, these will be the ones that are the influencers on Facebook, and these are there is the majority of the vertices that are not so popular, right? So those vertices around the boundary, they don't have so many friends, but there is a few important people that is, for example, in this case, this one, I don't know if you can see this, but there's lots of edges going into that vertex. Okay, and then you can see, for example, that there is, even though this graph is relatively dense, there is one guy, I don't know if you realize this, but this guy, for example, that is a loner, right? So this guy has no friend. And this is typical, right? This is not something which happens in other random graph models where everyone has more or less the same number of friends and everyone is then already connected. But here, this is a very popular guy here, but there's still some loners. And here you can see it even more clearly. There's smaller components, and here even more, right? But typically there will be one large component. Typically, if you think about alpha between 1/2 and 1, there will be one large component, which is this giant component, we call that. And that's where usually the interesting things happen. But there will always be a linear number of isolated vertices, for example. Okay. And then you can also change this intensity. This is just the only slide when we change the intensity. So if you change the intensity here, then it means if you make the intensity a bit smaller, then this ball here becomes a bit smaller. And that means that the same number of points here is in a larger disk, and here it's in a smaller disk. So here it's getting more intense. You get more connections here for the same curvature parameter here. Okay. No, there is no temperature here. No temperature. This is still the Sharp's threshold model, which makes an edge even only if the radius is if one is in the radius of the other. And that was the motivation of physics people. Why did this model become popular? Because they published in Nature they made this picture of Internet's autonomous systems in 2009, and then they made some maximum likelihood fit and said that, okay, if you incorporate a temperature, and then you can somehow see this as a hyperbolic random graph. But of course it's a bit weird, and don't ask me questions why this country here, Hungary, for example, is so far from Poland, or if Greece is so close to Australia. So, I mean, if you look at this in more detail, then you see here some kind of concentric circles, and the most important servers are close to the center, and then it's getting less important towards the boundary. But one should not overinterpret the geographic content here. Okay. Okay. So how do we analyze this formally? Well, one important issue of this thing is that since space grows exponentially, most neighbors are actually close to the boundary. So for example, if I look at a certain ball of radius I around the origin, and I look only at this strip of radius, of this annulus, of width 1, then in this layer Li, in this blue annulus here, I already see up to a constant the same number of points as in the whole ball here. And you can, it's this constant here that depends on alpha. So the measure of this layer is up to a constant the same as in the whole ball. Okay. Yeah, that's what I said. So most vertices are actually close to the boundary of this ball. And how do the balls actually look like? If you fix a radius capital R of the origin, well, then you get exactly the red ball. But if you look at the ball of radius capital R of a fixed point P, well, then this ball of radius R does not, in this representation, does not look like a Euclidean ball, but rather like this hyperbolic ball. And you see that the more P gets, the closer P gets to the boundary, the smaller gets this ball. But it always includes the origin, right? Because we said that the Euclidean, the hyperbolic distance from P to this origin here is always less than or it's exactly the radius, which is less than capital R. So it's always connected to the origin. We don't assume that there is a point at the origin, but if there were a point, then it would be connected to everyone. And this is monotonically growing. Okay. Yeah. So the degree is basically concentrated as a function of the radius, which is, so if you're not too far away, if you're not too close to the boundary. So if you're far away from the boundary, then the degree is basically a function of the radius, so the angle doesn't play a role here. This is not so hard to compute here. And if you're close to the boundary, okay, then you can have 0 vertices or 1 or 2, at most log n, but not more. Okay. And similarly, if you want now to look at where the neighbors of a typical vertex are, well, then you can just compute this according to these numbers, but forget about the numbers. The numbers are not so interesting here. If you take a point here, okay, you can say, look at a certain fixed intersection of this annulus of the ball of radius I, or the width of this Li here, and you want to know how many points are there. Well, you just compute the measure, right? It's a Poisson process restricted to this annulus, and you can compute it, and it turns out that that this function depends, that this grows as a function of I. So what does it mean? So it means that although here this looks very small here, if you're the point P here, most of your neighbors will actually be here, right? So this looks big here, this area around the origin, but there is basically nobody, or there is very few vertices, and the constant fraction of your neighbors is really in this small area close to the boundary, right? So this is thanks to this exponential growth. Yeah. So what is known about this model? There's many results known. I'll just give a few results here, namely that the degrees follow a power law distribution with an exponent between 2 and 3, depending on alpha. So alpha appears in the exponent of the power law. The average degree, which means the average number of friends of a vertex, is just 5 or a constant for these values of alpha between 1/2 and 1. For the same range of alpha, it's known that there is always one large component, one giant component, which has a constant fraction of all vertices. So we call that, which is written here, which is theta of n. For example, Tobias Müller has results on this. But there's always a constant number of isolated vertices, a constant fraction of isolated vertices. And much more is known. So this is just a very small and incomplete summary of what is known. But okay, that's maybe the most interesting consequences and known results. What we do now here is that we introduce dynamics on this model where vertices can move. So the idea is that vertices will perform independent Brownian motions and simultaneously the graph changes as well. Right? So let me explain this. What is our dynamic random hyperbolic graph model? So we say that vertices move independently from each other, but we want the spatial distribution to be invariant in space, in the sense that the number of vertices at a certain time, at a certain radius around the origin, is still in expectation the same. So we don't want to have a drift towards the boundary, neither a drift towards the center. There will be some drift for each vertex towards the boundary, but on average, if I look at a fixed snapshot at a fixed time, then they should behave exactly the same way as in the beginning. So we want to keep this spatial distribution which we have initially invariant over time. And what is the choice? How do we model the movements of vertices? Well, we say they move in the ball of radius r according to diffusion process, which has one angular component and one radial component. So for the angular component, there is no drift. So if I have a point here, well, then we have a Brownian motion for the angular component, which has no drift, right? Which can go either way. There's no drift towards a particular direction, since everything is angularly symmetric, which is the second part here. So there's this part here. I'll explain that in a second. And then there's a radial part, which is this part here. So since we have a drift towards the boundary, namely in the sense that there's many vertices here and very few here, for each vertex there should be some drift towards this boundary as a function of alpha. So this hyperbolic tangent, you can think of it as 1. So for each vertex there will be always a drift towards this boundary. But of course, if the vertex hits the boundary, then it's reflected, right? So it should not fall out of this ball. And then at each time the graph changes, because if the graph is at each time defined by the positions, so the construction of the graph at each time is exactly the same, in the sense that for each fixed time the edge between the two vertices is there if and only if at that particular point, at that particular moment of time, the distance of these two vertices is at most r. Okay? Okay, so what is the exact choice of our generator? Well, we have this, as I said, this diffusion process, and we introduce a new parameter beta here. So we have on the one hand this parameter alpha for the drift towards the boundary that is naturally given by the model, which is the curvature. As I said, the larger alpha, the more drift towards the boundary. So this is alpha over 2 here. And then there is this beta that is incorporated in this Brownian motion for the Brownian movement for the angular part, where beta is now a new parameter, with the idea that, okay, we have here this angular movement, and then we have this radial movement, but there should be some flexibility that how in the sense that how fast is the angular movement with relation to the radial movement, and that's given by this beta here. Okay, so this beta is a positive number, and you can see that the way we set it up, okay, for larger beta, this becomes smaller here, so the angular component is becoming slower than the radial component. Okay, so we will see that there's a relationship between alpha and beta that tells you which movement is more important. Well, as I said, if alpha is stronger, there's more drift towards the boundary, and if beta is larger, then this kind of angular movement here is slower. Okay. And we'll actually, since we talk about asymptotic results here, and there is basically no point very close to the origin at any fixed time, we can simplify this and say, okay, this hyperbolic sine is basically an exponential, and this hyperbolic tangent is basically 1, so we have a bit simpler generator to work with, and we'll work with this one. Okay, what are we doing with this model? Well, there was a paper by Yuval Perez, Alistair Sinclair, Per Lassusi, and Alexander Stauffer that looked at mobile random geometric graphs, but in the Euclidean space, not just plane, where it was a bit easier in a sense that they had just standard Brownian motion for each vertex. And what did they look at? Well, they looked at different properties. So in particular, they looked at the following random variable, which is called the detection time. So they said, okay, let's put an artificial vertex, Q, that might be outside all balls of radius r of all particles, initially or not. And let's say, when does the first vertex fall into the radius of this ball Q? That's the moment where we say, okay, this artificial vertex Q is detected, and we call that moment the detection time. Okay, so they studied many other parameters, such as the detection time of certain intervals or broadcast times. We will focus only on this part, but because we already struggled enough with Brownian motion in this context. But exactly that particular random variable we are also interested in. Okay. So what was their idea? Okay, their idea was you add some point Q, say at the origin if you want. And here is the radius, which is so-called the detection zone, or where the neighbors of that vertex Q are. And then you have these red and blue Brownian motions of all these vertices here. And the very first vertex, when that kind of enters this Q, which for the moment, suppose this is fixed and does not move, only the other vertices move. Then the very first vertex that one of these blue or red curves touches this sphere, then you detect this point. And it turns out, okay, that's a thin Poisson process. Well, what's the measure? The measure is, okay, the probability to start at a certain point, and given at that point, given that you start at that point, what's the probability that this detection time is less than t? That's the intensity of vertices detecting by time t. Okay, so it's a thin Poisson process with this measure. Or in other words, you can say, what's the probability that you don't detect by t? Well, you integrate over all positions, and you want to know that this thin Poisson process gives you 0, and that's the probability that this thin Poisson process gives you 0. Okay. And but what's nice is, okay, you can, if this vertex Q does not move, in fact it's the same as saying, okay, the other one doesn't move, right? So there's a kind of a, if you say this x0 vertex that starts here does some Brownian motion and enters the sphere of Q, that's the same as if Q actually moves and enters the sphere of x0. So what was nice for the paper of Yuval Perez and his co-authors is that they could therefore express this probability that you detect by time t as a function of the volume of the Wiener sausage at time t, which is well known, right? So the Wiener sausage is basically you do some Brownian motion of all vertices simultaneously. You do a certain tube around this movement. So here you have some Brownian motion of some vertex that might intersect, and then you do in this model a tube, so you kind of blow up this, and you get this area corresponding to the radius, and you want to know what is the volume of this area as a function of time, and that's well understood in the Euclidean case, and this expected volume is as a function of the dimension. It's explained here. And that's well known for the Euclidean case, but at least as far as I know, it's not known for the hyperbolic case. And that we cannot do the same thing, unfortunately, because we don't have such connection to the Wiener sausage. But nevertheless, we managed to give some tail bounds on the detection time for hyperbolic graphs. So this is the theorem that we have with Markus Kibi and Amitai Linker. Yeah, don't. This is horrible. Don't look at it in detail for now. But what does the theorem say? Okay, it says if you have some alpha parameter and some beta parameter, then depending on the ratio between alpha and beta, the detection times or the tails of the detection time behave differently. Okay, so roughly speaking, it says, okay, if there is alpha and beta like this, and there is a relation between alpha and beta, and the time is maybe not too small and not too large, then the tail has some form which looks like this. Okay, that's the result, and I'm gonna in the remaining time explain a bit in detail where these results come from. Okay.
So the particles, you don't care anymore about the interaction between them, right? They only look for one detector.
Yes. So there's only one artificial vertex that we add, and even we make it even simpler. This artificial vertex does not move. It's one vertex that is at the boundary of the sphere. Say here, this one does not move, so it has some sphere of influence, and all the others move. So it can happen that already initially someone is in there, then the detection time is 0. But if not, then you look at the first moment when some of these vertices outside falls into this ball.
It's basically the first heating time of a large set of particles in this reflected sphere.
Yes, yes. And it's obvious, it's intuitively obvious, right, that the first one that will fall into this sphere will be someone that initially is rather close, right? So it's not someone that will be here, but it's someone that will maybe be here or here or here. So there should be a kind of a danger score for a vertex, or an importance score, if you want, of a vertex, depending on its closeness of the of that vertex originally, which does not move, right? So this vertex is really on the boundary and stays there fixed, and we want the first one. We want to look at the first vertex that that detects this guy. Okay. Okay, so to understand a bit this proof, let's make it a bit simpler in the beginning. So let's suppose that we have only an angular component or only a radial component. So if we have only an angular component, only this generator here with no radial drift, well then it's Brownian motion without reflection. And in each moment we know how it behaves. So if you look, for example, during time t, how far do we move from here? If you're at this time here at a certain radius, so the radius does not move. You always stay at radius r in this model. There's always this small r that does not change. In 1 unit of time, this is this e to the minus 2 beta r generator. Well, it's known that standard Brownian motion up to time t will displace root t from that origin, right? So it's basically the square root of the time that will be your maximum displacement from the original position. And if you don't have Brownian motion 1, but if you have this e to the minus 2 beta r, well then you take the square root of this and also the square root of the time. So that's the maximum displacement in angular distance that you will reach by time t. Okay. So then one might think, okay, so then all vertices that have an original angle theta 0 smaller than this, they should have a good chance to actually detect the point Q by time t, right? So we define a detecting set, which are all those vertices that have the original angle smaller than that. They are kind of the ones that have a high danger score. The other ones rather not. Okay. In particular, it contains all points close to the origin, because as you can see, so if the radius is large, if you're very close to the boundary, then you move much less. So the picture that I should say is that if you point here, this vertex angularly moves maybe like this, but someone here has only a very small movement typically, right? So if you're further, if your radius is larger, if you're closer to the boundary, then you're moving less. If you're far away, then you have this kind of larger swings. And then, which means that this detection area, or this detection set dt, is this shaded gray hyperbolic ball here, looks like this. Okay, so inside this shaded area, we have like constant chance to detect by time t. So this shaded area grows as a function of t and has this shape here. Okay. Okay. Now what if you have only radial movement? So if you have only radial movement, then we have here's a point here. The point moves only radially, so it can only move in this direction. Does not move angularly. There's always a drift towards the boundary. And what can happen? Well, basically, what we look at is the following. Okay, this vertex it will typically drift towards the boundary, but there will be some moments of time where he'll go upwards from he'll go away from the boundary, right? So he goes maybe there, then stays for a long time there, then a bit further away, and there will be one maximum excursion, which is kind of its most important point, which is the furthest away from the boundary, or the closest to the center, that he'll reach by time t, and that's where he has the highest chance to detect, because its distance from this point Q here is the smallest one here, right? Remember that if he were at the origin, he would exactly detect Q. So if he's not, then he will be looking for its maximum point, and there it will be detecting or not, right? And one can compute the time, or one can compute the maximal distance from the boundary, and say, okay, and it turns out that in time t, the point closest to the center, closest to the origin, in expectation has this radial coordinate r minus 1 over alpha log t. Okay. If you think about it in terms of angles, well, this means that if I'm reaching this height r minus 1 over alpha log t here, well, then I shouldn't, and I want to know if I detect here, then I should not be too far in terms of angle from this point here originally. And if you convert that, it means that this angle should be at most 1 over nt to the 1 over 2 alpha. Okay, so it means that you will have a certain region again around this point Q, which has a good chance to detect this point. Because if you were here, okay, you will also reach the same height, but at this height you will still not detect. Okay. So then we can similarly define a detecting set, which are all these points which have an initial angle of at most 1 over nt to t to the 1 over 2 alpha, and in the figure this looks like this, right? So these are all these points that are in a certain area, like in a certain hyperbolic angle that might detect. Okay, that's the angular. No, sorry, that's the radial movement only. And now we combine these things. So now we have a radial movement and an angular movement at the same time. So where are the detecting sets? And there it turns out, well, it depends who is more important, the angular movement or the radial movement. There's this alpha parameter, which is the drift, and there's this beta for the speed of the angular movement. And what do we observe? Well, we said that the angular movement has in the generator a part which is e to the 2 minus beta r. So we know in each layer, if we were exactly at radius small r, then we would know exactly how much variance in angular terms we would have. We know that we maintain the distribution of the points invariant, so we know how much time typically we'll spend in a certain layer, because we know the density of a given layer initially, and this doesn't change over time, so we know that during time t we expect a time which is t times the probability that you're at that radius plus minus 1 originally, so you know how much time you spend in expectation at a layer r. And this, you know, this time here, t times e to the minus alpha r minus r. So you know the kind of expected angular variance that comes from the time you spend at this particular radius, which is just for one moment of time multiplied by this time, which gives you this total contribution of the variance at that particular radius. Okay? Well, now, this could be increasing or decreasing in small r. We don't know that, right? It depends on the regime. It depends on the relation between alpha and beta. And observe that if alpha is larger than 2 beta, okay, then this is positive as a function of r. So that means the main contribution comes from the boundary. What does this mean? This means that if you're a vertex here, okay, this vertex, it will spend most of the time here. From time to time, it will go also further up, but it spends so much more time here, so that although this variance here is much smaller than this variance here, the contribution of this variance here is more important than the other one. On the other hand, if alpha is less than 2 beta, okay, then yes, the vertex will spend most of the time here close to the boundary, but there will be some moment of time where he reaches very far, he goes very far away from the boundary, and at that point he has so much importance, there's so much angular speed that he makes, so that there will be the moment where he has the highest chance to actually detect the point. And if alpha is equal to beta, then all these different layers, they have the same contribution. So here you spend lots of time, here you spend less time, less and less, but this is kind of compensated by the fact that the variance is getting larger, smaller, and so on. So that's the explanation why different tail bounds appear for different values between alpha and 2 beta. Okay, so this is maybe a bit technical. I will skip this part perhaps. Yeah, for the alpha equals 2 beta case is maybe the technically hardest one. One computes the probability, one computes the expected time that you spend up to between at a certain radius between 0 and k, for example. This is the expected time, and then we do, well, of course there is dependence between different times. So if you're close to the origin at one moment, then at the next moment you're still there. So you cannot just say these are independent these times, but we do some weak concentration in the sense that the probability that you spend at least a constant fraction of your expectation is at least a constant by some coupling with a discrete process. And we can also actually then show how where these points are that detect. It turns out that if beta is larger than 1/2, then the angular component is of so little importance that we actually detect by radial movement only. And then this means that the detection set again has a different shape. So we can in all cases clearly say geometrically where are the points that they have constant chance to detect, and we can also control the points that are outside this detecting set. So if we are at this blue point, for example, we can say this blue point will not have a good chance to detect this red point Q, because radially he will not exit this box. So think about this black part here is a box. He will not exit radially, and he will not exit from the side either. Yeah, the probability to exit from above, we control that, and to control the chance to exit from the sides, well, there's a picture here. We split kind of the radial trajectory into excursions, and then we have kind of a law of large numbers of these different excursions. The very first one is a bit different, and we see that it also doesn't exit from the side. Okay, but maybe I'll stop at this point. Okay.
Are there any questions?
Is anything known or conjecture about the dynamics of the spectrum of these moving graphs?
The spectrum of these graphs?
Yeah, about like if anything is known or conjecture.
For the static model,
the dynamic model.
No, I think as far as I know, there's no other result on dynamic random hyperbolic graphs. So I only know there is a result for the spectrum of the static case, which tells you that the spectral gap, or the second of the largest component, is n to the is some power of n, n to the 2 alpha minus 1, I think. So that's known. It's known what the mixing time of a random walk, the cover time of the random walk in the static cases.
Yeah.
The commute time, I think, also, but only for the static case.
Okay.
For the dynamic case, as far as I know, there's nothing else known.
Okay. Thank you very much.
In your talk, the radius r was always fixed, I think. Or
No, the capital R is it was a function of n.
Okay. I completely missed that. Sorry.
So it was I put it basically like
Okay,
2 log n.
Okay.
So it was
Thank you.
in a limit. You can think about it as the whole plane.
Okay.
More questions?
Are there still some mysterious open questions on the geometry of your random hyperbolic graphs, or not?
Some what?
Some mysterious open questions on the geometry of random
Of the
hyperbolic
static
graphs?
model or of the?
On the static one. Here is one, I don't know if it's known or not. If I give you the graph, can you recover or partially recover the spatial embedding? I give you only the graph structure.
You give me the adjacency matrix. Say.
I give you the adjacency matrix. Can you what can you tell me on the underlying geometry?
Yeah,
I mean the embedding.
Okay, so this is. I think this is. I'm not sure if there are some results, but I think this should be doable in the sense that, okay, first, well, do you want perfect or approximate? So, I mean, you know, if you have vertices that have just one, isolate the vertices, you put them wherever you want. So first you would then look only at the, yeah, sure, but at the boundary you could put them where you want, right? Then there are these degree 1 vertices that still have a certain freedom. But for the others, well, I would embed, say, I would start embedding with the highest degree vertices, right? Because the degrees basically tell you how close to the center you are. And
For example, the center one, can you pinpoint to which precision can you pinpoint its location in the hyperbolic plane?
Well, if you start with the center point, that corresponds to the fluctuation of the degree, right? So there will be a small fluctuation of the degree, but this is of not so high order. So that will be the fluctuation of the radius. And if you start with this one, well, this first vertex is angularly symmetric, so you kind of find an annulus of that vertex where you so you know the degree, then you know the radius more or less, so there will be some small fluctuation, and then you kind of know that it's on this annulus, and you can embed it wherever you want by angular symmetry on this angulus, right? And then, okay, then you can continue in the sense that maybe with next points, then you can, if you have the next point, okay, where will you put it? Well, it will depend on the common neighborhood. So you can, I think it should be not so hard, because you look at this point and the next point. Okay, if this point and this point have lots of neighbors, then this tells you something about this angle. If the neighborhood of this is small, meaning that there's only high degree vertices that are there, then maybe it will go somewhere there. I'm not sure if this is known, but it should not be so hard, I would guess, up to these errors that you have to accept.
More questions? Okay, if not, let's thank Dieter again.